Okay, welcome everyone to the ZAG Zoom Algebraic Geometry Seminar. We're very pleased today to have Lawrence Barrett from Leiden, and he's going to talk on fibrations and degenerations of Calabi-Yau varieties via tropical geometry.
I'd like to begin by thanking the organizers, of course, for inviting me. And this topic roughly goes under the title of the Duran-Harder-Thompson conjecture. But since Duran was the person who invited me to talk, I didn't know if I could, seems a bit self-congratulatory to include this in the title. Okay, so I'm going to talk today about some work which is joint with Chuck Duran, and it's also part of a continuing project, series of conversations I've been having with Andrew Harder and also Fenglong Yo. Okay, and it's going to be a talk in approximately 3 parts, 3 sections. And the first part of this is going to be some sort of philosophy of the DHT conjecture, which is what this is going to be about trying to prove. The second part is going to be some discussion about deformation algebras, and Bogomolov-Tian Todorov theorems. I'm going to write out those names a bit later, but now I'm just going to write BTT. And the third part is going to be sort of assembling ingredients. At this point, I would just also want to pause to say a lot of this talk uses a lot of very hard results due to a wide collection of other people. And I'd really like to thank those people that I'm going to mention in advance for having done somehow a lot of work without which this project wouldn't have been able to happen. So there's this group in Hong Kong of Chan, Leong, and Ma, whose names will appear. Also, Philippe Felden and Rudat provided sort of the other half of this. And in the background, this is all occurring within something called the Gross-Seibert program. So Gross and Seibert also will appear a lot in this talk. I really want to thank all of them. Okay, so start with section 1. So now, as we must, it's going to be talk about the philosophy of mirror symmetry and why you would come up with this thing called the Duran-Harder-Thompson conjecture. So mirror symmetry sort of comes in 2 flavors. If people struggle to read my handwriting, then they should please say. But I think it's better than on a whiteboard, on a blackboard form. Okay, so mirror symmetry comes in 2 flavors. There's something which is called, say, Calabi-Yau, Calabi-Yau. I'm going to say, I see it's somehow a topic of research that appears a lot, but I'll say briefly what we mean by this. And there's also going to be something which is Fano pair, Landau-Ginzburg mirror symmetry. So these are the 2 flavors that exist, and I'm going to also just need to say that for us, so this is a definition of Landau-Ginzburg or LG model. Is some proper morphism and it's going to be a proper morphism W from Y to A1. And it's going to have Calabi-Yau fibers. And maybe with some normal crossings singularities. So a normal crossing singularities on some fibers. So not all of these are smooth, but they will, even where they're not smooth, they will have trivial dualizing bundle. In that sense, they're Calabi-Yau. Okay, so what does mirror symmetry say? It says that to anything of the left-hand side, to any degeneration of an object on the left-hand side, we should be able to construct a family of things on the right-hand side. So to any degeneration of a pair of Fano and an anti-canonical divisor on it, we should be able to construct a family of Landau-Ginzburg models which interchange in an appropriate sense data coming from physics. Or similarly for Calabi-Yaus, given any degeneration of Calabi-Yaus, I should be able to construct a corresponding family of Calabi-Yaus on the right-hand side, which interchange in the B model, but that's not going to be so relevant for what we're going to talk about today. But the idea is that, so mirror symmetry and what it really works for are semi-stable degenerations. So xt maps to A1 upper one. So rho is smooth, rho is flat. Xt, the whole space, is smooth. The generic fiber of the family is a smooth Calabi-Yau, or smooth Landau-Ginzburg pair. And the central fiber X0 is the union of normal crossings divisors. And we're going to ask one further thing, which is a maximality condition on X0. We want it to be as degenerate as possible. The way that we're going to encode that is such that there are a collection of components of X0, so each collection of these divisors intersecting only in a single point. So we're going to call this notion maximum. And examples of these things are pretty easy to come up with if I take quintic hypersurface inside P4 and then degenerate it to the boundary, I'll get something whose total space has some singularities, but then I can resolve those singularities and I'll get such a degeneration. Okay. So examples. Degenerating toric hypersurfaces. Then resolving the total space. Oh, sorry. I meant to say to the boundary and then to the boundary. Okay, so if I wanted to draw a picture of this thing, I would have some sort of nice, smooth calabi-yau, and then it's degenerating into the union of a collection of pieces. So picture of A1 is 0. Okay. Right, so to such a thing, we should be able to construct a mirror family of calabi-yaus, or if I have a degeneration of pairs, I should be able to construct a mirror collection of Lerner-Ginsburg models. So to such data, we should construct a mirror family of calabi-yaus / LG models, depending on which side we're on. Okay. Right, so that's very good. We've looked at these very maximal degenerations and then claimed that we have some way to construct some associated spaces to them. So rather than looking at very complicated degenerations, we could look at the simplest degenerations possible, because we'll see that they provide a bridge from calabi-yaus to Farnhams. So where do calabi-yaus and Farnhams meet? And the answer is in Turin degenerations. So definition. A morphism xt to A1 is a Turin degeneration if the generic fiber is a smooth calabi-yau, the total space is smooth. And if I look at the central fiber, then I have the union of two components, Z1 and Z2. Now, these things obviously aren't maximal if the dimension is positive, if the dimension of their intersection is positive. So we have Z1 and Z2, and these are normal crossings. And the relative dualizing sheaf is trivial. Which actually, I think is actually already implied by the previous things I've said, but I should be specific about it. Okay. Right, so we should want to observe some things about this case. So we can not just look at Z1 and Z2, but we can look at their intersection. So Z1 intersects Z2. This thing is necessarily anti-canonical. On Z1 and Z2. The Zi themselves are smooth. So by adjunction, sorry, XD, Zi are smooth. So by adjunction, D is also Calabi-Yau. D is also Calabi-Yau, also has trivial dualizing bundle. Its dimension, of course, one lower by counting. And there's also another fact that we know, which is that the normal bundle of D inside Z1 is the dual of the normal bundle of D inside Z2. So Friedman's work on D semi-stability implies, if I look at the normal bundle D inside Z1, this is the normal bundle of D inside Z2. Dual. Okay, so what we can think of this as being is a way to go from smooth Calabi-Yaus to pairs of a variety and an anti-canonical class, anti-canonical divisor on it. And those are the sorts of things which live on the left-hand side of the Fano pair Landau-Ginzburg mirror symmetry. Right, so we now have a bit of a problem. So I said that it's Fano pairs. So that implies that D should be ample. But because of this relation, if D is ample on Z1, it definitely can't be ample on Z2. So let's just make a remark. So we can assume sorry, we can't assume D is ample on both sides. Yes, unless one of these is a point, unless D is a point or something. So we'll assume that it's ample on, well, we'll assume that it's at least Nef on Z1, which is an assumption. And that's going to be necessary to apply the mirror constructions that we know exist. Okay, so we have these two different types of degenerations, and we can ask, well, where do they meet? And we're going to force them to meet by considering a family. So combine them into a family. So we're going to assume that we have XS comma T, which is a family over A2 now. We can call this thing rho AS comma T. So we're going to ask that rho is flat. And also that rho is locally isomorphic. To something of the following form. So S goes to the product over I inside I, yi. The size of I is less than or equal to 2. T is going to the product over I inside J, xi. And now we have no constraint on J. And what we ask is that x, s comma t, is locally isomorphic to spec k adjoin the yi's, the xi's, and maybe some extra free variables. So in particular, it's smooth and it's locally isomorphic out space. So this is a bit of a wordy way of saying that this thing is a log smooth degeneration without having to introduce the terminology of log structures. But really, it's like a semi-stable degeneration in the sense that here you can see the local structure of the semi-stable product. Okay, so in particular, we also will ask that for, and I have to always check to make sure I get this the right way around. So for t fixed non-zero, we have a Turin degeneration. I'll draw a picture in a second as to what this is supposed to look like. And for S fixed non-zero, we have a maximal degeneration, maximal semi-stable degeneration. Okay, so just to draw a picture, here's my base A2. I have two axes. Now, if I look at the fiber over one of these axes, I see two pieces. I have D, Z0 and Z1. Over here, I have some sort of very complicated thing which has individual points living inside it. That would, I think, be okay as an example. This is maximal, this is Turin. And we want to really look at where these things collide, which lives down here. And I can't draw a picture of it because I picked too complicated a picture for the two sides. But the idea is that these two different types of degeneration are going to meet. And you can ask, in fact, this thing is itself maximal. So what does mirror symmetry have to say about it? Okay. So the important thing for us is that this forces, so we have our D here, we have our Z0, and we have our Z1. This actually gives us, forces on us, a maximal degeneration of these three things. So we get for free maximal degenerations of Z0, Z1, and D. Okay, so D is Calabi-Yau, Z0, comma D, say, is a Fano or Neff pair, depending on how adventurous we're feeling. Right, so the expectation from mirror symmetry is that from this data, we're going to construct a formal smoothing of a very sort of singular scheme. So from this data, we should get a formal smoothing of a singular scheme. So governed by tropical geometry. So in particular, the statement that we're going to extract from this is that the relationship between the two sides should be the relationship between, on one side, the intersection complex of this very complicated central fiber, and on the other side, the dual intersection complex. So it should exchange the role of the intersection complex. I'll see, define in a second what this is. Intersection and dual intersection complexes. Okay, so what are these things? So definition. Given this data, start off with the dual intersection complex. This has one point for each component of the very central fiber, so the fiber over the origin. And any collection of points are connected if and only if their intersection of the corresponding components is non-empty. So that gives you some sort of simplicial complex that you can work with. So points are connected if the intersection of the corresponding components is non-empty. It's the intersection of the components is non-empty. Okay, so this gives you the dual intersection complex. The intersection complex is defined in an analogous way, but rather than having 1 point for each component, we have 1 point for each maximal singular point. So the intersection complex has 1 point for each maximal intersection. And then connected if there is an intersection connecting them, if there is a singular strata. Okay, so that's kind of a wordy definition. It's much easier to draw a picture of what happens in this case. So in this example, in this particular example that we're talking about, what one would end up with is something which looks like, try to get this thing. Oh, I have colors. I can use colors. I'm going to do this part in red for reasons which will be about to become clear. So this is, let's say, this is the intersection complex. And then on the other side, well, every vertex here gets replaced by a component, and every component gets replaced by a vertex. And if I've drawn this correctly, thank goodness, I spent some time practicing drawing in at least somewhat convincing 3D models. Um, 1, 2, 3. You have something else over here. Okay, so this is then the dual intersection. Okay, now I drew this part in red, importantly, because the red part is the intersection complex of D. So we said that we had an additional degeneration of D hanging around. So this has a corresponding intersection complex. And it appears here as separating our space into two components. But then on the other side, the part which I'm going to try to shade, this part here. Because of the way that duality works out, this part here is the dual intersection complex of D, but now cross a unit interval. And potentially longer than a unit interval, but topologically cross a unit interval. Okay, so this is supposed to be the model for what is happening, at least on the very central fiber of our smoothing. And what we have here is a space which, at least before we try to smooth, has an open subset which is isomorphic to the dual intersection complex of D cross 0, 1. So if we reconstruct the corresponding space, so the corresponding unsmoothed singular scheme is fibered and is fibered by things whose intersection complex is the dual intersection complex of D. So it's fibered by things which are mirror to D. It's fibered by things mirror to D. Okay, so we're now ready to actually state the sort of theorem that we're aiming to prove. So conjecture, which is one part of this de Reinhardt-Thompson conjecture. The mirror to such a degeneration is a fibered Calabi-Yau whose fibers are mirror to D. This is sort of the justification for it, is this picture here. So there's a bit of a problem, which is that everything that I've said so far, I've used the phrase semi-stable degeneration. And in fact, this conjecture isn't so hard to prove if you ignore the final part, whose fibers are mirror to D. You can show that the mirror is fibered if you work with modern techniques from the Gross-Seibert program, the problem is that you don't know that the fibers themselves are anything to do with D. And you have to work quite hard to be able to make any statements at all. So problem, we don't work with semi-stable degenerations. We have to work with what are called simple toric degenerations. Use simple toric degenerations, not semi-stable. So these are degenerations which locally look like the degeneration of a monomial inside a toric variety onto its boundary. And the simple here has to do with the vanishing of certain differential forms. It includes examples coming from toric hypersurfaces in particular, which is most examples that you'd think about. Okay, so section 2, which is deformation algebras. And classical deformation theory says the following things. By classical, I mean it existed before I was born. So if X is a smooth Calabi-Yau, D contained inside X is another smooth Calabi-Yau divisor. CY divisor. Importantly, not a curve. Dim D, I'm going to assume bigger than 1, then the following things hold. Deformations of X are unobstructed. That doesn't require anything about D. This is the Bogomolov-Tian-Todorov theorem. Okay, part 2. Every deformation of X lifts to a deformation of the pair. So deformations of X. Of the pair X comma D. And the third part, deformations of D inside X are unobstructed. Since I don't have so much time, 2 and 3 are just saying that the normal bundle of D inside X is trivial by adjunction. And since D is Calabi-Yau, H1 of its structure sheaf, so H1 of its normal bundle, is also is 0, is trivial. And so there are no obstructions to deforming D. And 3 says that X itself is fibered and it's a map to P1 because I can deform the defining equation of D to some other equation, and it gives me 2 sections of my line bundle, so a map to P1. 2 says that any small deformation of X is also going to be fibered, so the entire component of the Calabi-Yau moduli space containing X is going to be fibered. 1 is the interesting and hard thing. So many proofs of 1 and somehow the one which is most interesting for us is using the fact that the polyvector field algebra, the sheaf of fully vector field algebras. So I take the direct sum of the wedge powers of the tangent bundle of X. So in general, this thing is a differential graded Lie algebra. It's a Gerstenhaber algebra. So it is not just Gerstenhaber algebra. But a BV algebra. So I'll say what BV is, Batlin Dolkovsky. So what do I mean? Well, this thing here is naturally an algebra because I can multiply together elements of it, and I just take the wedge of the corresponding elements, and it has a Lie algebra structure coming from the Schouten-Nijenhuis bracket. But from the fact that X is Calabi-Yau, I can identify these things with the differential forms, so the wedge powers of omega. And on the wedge powers of omega, I have the de Rham derivative, de Rham differential, and so I can transport that along the comparison, i.e., we have a positive graded operator delta with d delta plus delta d is equal to 0, where this is the Schouten-Nijenhuis. Okay, and then the proof continues. So given such structure, the deformations are unobstructed if you can show that the following things are constant. So if hi of wedge j of tx is constant in families. So i.e. the Hodge bundles are actually bundles and not just sheaves. So let's call this Hodge freeness. Okay. And of course, if things are smooth, you have a million ways to prove that this thing is constant in families, and you can just choose your favorite. Okay, I see that we're sort of running through time quite quickly. So let's talk about somehow the ingredients. And this is where the names that I mentioned at the start come in. So this is all for things which are smooth. So Chan, Leung, and Ma gave a construction of what they call an almost BV algebra structure on even on singular Calabi-Yaus, assuming, for instance, this Hodge freeness result. So they showed that they gave a construction of this thing, so showing that the deformations are unobstructed, unobstructed, assuming Hodge freeness. And some other small things, so local models, local uniqueness of the deformation theory, and also degeneration of the Hodge to de Rham spectral sequence, which actually, in nice cases, implies Hodge freeness. So although it's a separate assumption, not necessarily needed. So now this other group that I mentioned, so Philippe, Falson, and Rudat, showed that these assumptions held for the output of the Gross-Seibert program applied to our two-dimensional family XS, T. Okay, so they showed, as I said, that you have this degeneration of Hodge to de Rham, and Hodge to de Rham spectral sequence degenerates. Okay. So that's the output. And so you can apply each of these to X, to the output of this thing applied to X and to D separately. So we can form X check and D check separately. Using these techniques, we have a very singular scheme with some additional structure, and then we can smooth them because we know that the deformation space is unobstructed. But we don't know how to smooth them together. So keeping D check as living inside X check. And of course, the answer is that these things work by applying these techniques to, let's say, differential forms on X check with log, with the log structure involved, and D check with some sort of log structure involved. But we really want to apply them to the algebra of vector fields, polyvector fields on this central fiber X check, but which vanish along our choice of D check. This is vector fields preserving D check. And why is that? Well, this polyvector algebra D check, if I give you something which preserves D check, it gives me a polyvector field. So this thing admits a map to the thing which we can smooth to get the family associated to X check. It also, of course, admits a map to vector fields on D check. And so if we know that deformations of this coming from this are unobstructed, well, then we can map them to each of these and so deduce that actually we can embed D check still inside X check. Okay, so to apply this, so to apply these techniques, you need to show that all of the operators, so taking Nine-house skeleton bracket and taking multiplying together vector fields and also taking this BV operator are compatible between all of these. So we need to show that Tx log D is a BV algebra. All the maps are maps of BV algebras. Really, I should have a wedge inside each of these. So all the maps are maps of BV algebras. And then the third part, if I look at the rank of the cohomologies of these, these are stable. So these are constant in families. So the appropriate Hodge to de Rham sequence degenerates. Okay, 1 and 2 are local calculations. To get the BV operator, you restrict the one from this object to here, and you show that it preserves the condition of being 0 along D. 2 is that it's really just local computation everywhere. Part 3, to show that this thing is constant in families and that the Hodge to de Rham spectral sequence degenerates, uses a very old result from Glean-Lucie's paper, relèvements modulo p squared et décompositions de complexes de de Rham, which weirdly hadn't appeared in English. You can find a proof in the first paper with Chuck. Translate, and it's their proof, but translated into English. It was interesting that it hadn't appeared. So 3 uses a variant of corollary 4.1.5 in Deline-Lucie. They give a very powerful criteria for when the Hodge to de Rham spectral sequence degenerates, and they show that that actually implies that these things are free. Okay, Chuck, when do I have until?
Yeah, I mean, technically the hour, but we're virtual, so I don't really care.
Sure. Well, no, so I timed it to the hour, and I'm doing okay with this. Right, so in total, this leads you to the theorem, sort of the main theorem of our paper. And I'll state what it is, and then I'll say that actually what we prove is something slightly stronger. So the end result is, suppose x s comma t mapping to A2 is a simple, what we're going to call a simple toric-Turin degeneration. With D, I think in my notation is going to be dt, the corresponding the generation of the Turin locus, Turin singular locus. Then the mirror X check is a fibered Calabi-Yau. With fibers mirror to D. To this particular choice of degeneration. So the proof goes, once you build up all this machinery, I can deform free unobstructedly here, and then I take spec of the associated I take spec of the associated sheaf of algebras. Well, on the central fiber, that's isomorphic to spec of the associated sheaf of algebras once I map the deformation to here. And if I have two flat families which are isomorphic at a point, they're isomorphic in an open subset around that point. So that says that the deformations that we get on the top are the same. And we also have a map down from the sheaf of algebras coming from a solution of this BB algebra to the one here. And that's a surjection on the central fiber. And if I have a flat family of schemes together with a map between them, which is a closed embedding, then in a neighborhood, which is a closed embedding at a point, then in a neighborhood of that point, it remains a closed embedding. So that then says that indeed we can embed D check inside X check in some way. So we smooth them both off together at the same time. And once we know that they're both smooth, we can apply the classical results from deformation theory to say that actually the entire component is fibered, so fibered family of Calabi-Yaus. Okay, so there's one thing which hasn't entered into this picture, which is what the statement is relating the Landau-Ginzburg model to the fibration is. And that's quite a more subtle picture that's requires some additional constraints on D, and is sort of part of the ongoing project in some sense. Okay, I think that that's me finished.
Okay, let's thank Lorenz.